Good. Well, good afternoon. So, Glynn Williams, I'm speaking to you from Elstree, just north of London. I've actually got a mining background. I graduated in mining in 1977, and if you look closely at the photograph there, you'll see a picture of myself and also your current treasurer in that group that was taken during a field trip to a Polish coal mine in 1977, and the hairstyles probably look a little bit unusual today. I graduated, and then I joined a business that was assisting in the development of the Selby coalfield, and that company is now called British Drilling and Freezing. And I was involved in the shaft sinking, and we were doing the ground freezing work that had to be done in association with the shafts that were sunk into the Selby coalfield. And then in 1980, I got a little bit distracted into the oil industry. The oil price jumped up because of the Iran-Iraq war, and the oil services sector expanded hugely, and I joined Schlumberger and had an overseas international career with Schlumberger through up until the mid-90s. During that period, I became involved in fibre optics, and I'm currently the CEO of Silixa, and we are the global leading independent provider of fibre optic solutions, and we operate in the mining, earth sciences, environmental, alternative energy, geothermal, for example, hydropower, being examples of alternative energy, and also infrastructure and oil and gas sectors. And we've got quite a broad geographic footprint. We have operating centres in Houston and Montana, Calgary, Ontario, Chile, Beijing, and also in Australia. So let's see if I can advance this. Is that going to work? Oh dear. How do we get it to move? Any clues, Mike, on how we do this? There we go. Good. So we provide a number of solutions using fibre optics, exclusive fibre optics into the mining sector. So we're able to do moving from the top left-hand corner and then through the bottom and then up to the top right-hand corner. We're able to monitor slope stability. We're able to monitor underground rock mass stress and strain. We substitute seismographs, geophones, and extensometers using fibre optics as a new form factor. The technology is very robust and doesn't require power at the point of application. We also operate extensively in the copper sector, particularly with the bottom right-hand diagram, where we're able to retrofit or retrospectively create a non-intrusive flow measuring device by simply wrapping optical fibre around a pipe. And we can detect the vortices that are travelling through the pipe when turbulent flow exists. And this is a very cost-effective solution for retrofitting into quite complex flotation plants and get us a better understanding of the movement of fluids and mass pull throughout the system. And one of our flagship projects for that, of course, is with the new Anglo-American Quellaveco mine, which is part of their Smart Mine, Digital Smart Mine initiative. And the area I'm going to talk to in more detail today is tailings dams and the huge potential that exists for the application of fibre optics into understanding the behaviour of tailings dams. And we've got a very strong foundation of this work, which now reaches over a decade. And obviously, the common failure modes of tailings dams that have been recognised in the past are overtopping, obviously then a breach and loss of containment, seepage and erosion within the dam structure itself, that's water movement, and then instability due to excessive deformation within the embankment. And I've put a couple of other points under there, which I think may be more kind of forward-looking. We may have to use more foresight when we look to the future, because perhaps our new resources are going to be exploited in more seismically active regions. So is natural or induced seismicity going to be an issue that we need to understand more in the future? And then the other point is climate change. How do we anticipate changes due to the maximum design flood in the design of these facilities? Because the world is changing and there isn't probably a great enough understanding of the effects of climate change. So I think probably that is going to lead to the need for additional instrumentation on tailings storage facilities. A lot of conventional instrumentation is used in this sector, and a lot of it is complementary. And there's a good example here, which I've picked up from Chapman, published in 2021. And obviously, we're able to look at observe the issues of overtopping, internal erosion, slope stability, instability, and many techniques exist for this. I borrowed a slide from RST Instruments, who is one of our partners in North America, which shows a good graphic of the type of instrumentation. And we see there are opportunities working in this field, due to some of the challenges of conventional techniques, is perhaps reliability of electronic systems, maybe the cost of ownership across a long project of existing systems that are built on electronics, perhaps the sparse sampling that is provided by the conventional technology, relatively small, in some instances, measurement resolution, maybe millimeters or multiples of millimeters if we're perhaps using satellite techniques. And then in order to be able to create a dense enough array of measurement, a significant number of penetrations perhaps need to be created into the structure. And of course, the dam never lies still. It grows with time, and every time there's a dam raising, of course, the instrumentation needs to be adjusted or moved, and there's a lot of intervention related with this. So we see opportunities for the application of optical fibers to overcome some of the challenges with conventional techniques. But I'll show a summary at the end where I believe that we actually, to a great degree, complement many of these techniques, perhaps with the potential to substitute for some of them. Now, what is optical distributed fiber optic sensing? An optical fiber has small impurities in it, which allow light to be scattered back to a source of light. A box typically has a laser which sends a pulse of light into the optical fiber, and as it travels through the optical fiber, small reflections are created. And the way that I explain this to lay people is that if we are driving at night in a kind of misty, going back to North Shropshire, Mike, it's foggy. When I remember the 70s, when I'd be driving to see a girlfriend or something in the fog, you get some reflections from the fog particles coming back through the windscreen. Now, little speckly lights, and actually this is what we see in an optical fiber. And the character of the reflections are altered by either temperature, acoustic, or vibration is a simple way of describing what an acoustic signal is, and strain. And because these reflections occur at every point along the optical fiber, we're able to create a very dense array that allows us, let's say, to sample a change in temperature as little as every quarter of a meter along the optical fiber, or maybe a change in static strain of 50 centimeters along the optical fiber, and in the case of a vibration or acoustic signal, every 2 meters along the optical fiber. So it creates a distributed sensing array. And when we contrast this perhaps to conventional single point sensors, we're able to see, in order to create a large array, it's going to be, comprehensive instrumentation. But point sensing does have its weaknesses, because there may be events that occur between 2 point sensors that can't be detected by the point sensor, but will be detected by a fully distributed system. And we can make these measurements up to tens of kilometers. We operate in the deep water part of the Gulf of Mexico, where we're able to measure changes in acoustic response up to 100 kilometers away from the source where the box is. And I'm going to show an example where we have 40 kilometers of cable in an unnamed storage facility in Australia, where we operate these measurements over tens of kilometers. Very quickly, what does it look like? Well, it's very simple. we lay an optical cable at the toe or the heel or the top of the tailings dam. The cable is very robust. Very often we use military specification cables because they have some degree of armoring. In certain geographic areas, rodents like to eat the cables, so we have to make sure that they are armored. And the cable contains a number of optical fibers because we're able to make all of those measurements I described previously at the same time and the same instant and at the same location. So having multiple optical fibers in a cable allows us to do that. And the cabling, because it's essentially developed for other purposes, either telecoms or military use, they're actually quite a cost-effective cabling systems. So we trench them in to the into the environment, the infrastructure, and also we can also trench them into vertical boreholes too for specific points of observation. Now we have created a solution which we call Dam Pulse, and it is a tiered solution. And what it allows us to do is to monitor the whole entire dam very effectively. We create very high spatial sampling because we can sample depending on the measurement as frequently as every quarter of a meter. And we can program alerts into the system. And we're also enabled to give real-time processing and visual presentation of data. And of course, the bottom left-hand diagram here shows the optical cables laid around the area of observation brought into an instrumentation array. And I can build on this a little bit and show you how we create connectivity for users on the instrumentation. But being a tiered system, level 1 essentially is all about dam breach. And we use fiber optic attenuation for this. If we bend an optical fiber, you get light losses. So it's at the simplest level of measurement, and it allows us to detect dam breaches. It's a little bit maybe closing the stable door after the horse has bolted, of course. Then the next level is seepage. We're able to measure seepage through seasonal variation and distributed temperature. And for each of these levels, I'm going to show you a following slide which just builds in a little bit more detail, but still at relatively high level on each of these levels. And then level 3 is deformation. This is where we use the distributed static strain, the movement that is going to be measured by a cable when we get movement of the Earth and the environment around it. And then we then get into somewhat more sophisticated areas where we start to use geophysics. We use the ability to measure distributed acoustic information, which is essentially a geophysics tool. So we have passive geophysics and then finally active geophysics. And the difference between the two is that in passive geophysics, we don't require an external seismic source. The anthropogenic noise or the ambient noise around the area is sufficient to us. And then when we use active geophysics, we can mobilize perhaps a seismic source for a period of time to make the signals. And many of these measurements, if desired, can be continuous monitoring. So we're able to bring the information continuously and in real time into the instrumentation. But I kind of thought a bit about this last night and just reflecting a little bit on this kind of triangle. I think that the value, and of course this is all done with one cable, as I illustrated previously, but I think that the value is inverse. Is that the value created by moving from level 1 to level 5, I think is much bigger, because we then move from being observational to predictive when we're able to look at the activities delivered over levels 2, 3, and 4, and 5 with the system. So I'll just quickly pass through each of these levels one by one, just to give you a greater understanding of each of them. So level 1 is the breach system. So essentially what we have is a very simple module, which is constantly measuring attenuation along the optical fiber. And this then is able to detect a significant movement and behavior in the optical fiber. And this may be as a result of a breach. And we've got a number of activities, particularly in South America at the moment, where there have been some issues around actually the failure more of tailings lines than actually the structure itself. And when we place a temperature measurement device alongside that, we're not measuring temperature, but the temperature measurement device has a better spatial resolution so that we can detect the event to much a greater pinpoint along the optical fibre. It's a very cost-effective combination. The power requirement is very low, so we can operate this through a battery bank, which is powered either by turbines or solar, and then we are able to communicate data through RF antenna into the client infrastructure. So this is probably at its simplest, and it's very cost effective. I think we're marketing these into the market at maybe about $100,000 of capital expenditure, and then a subscription for support once the system is installed. And then we go beyond that to level 2, and this is where we then use the same distributed temperature sensor that is inherent in the dam breach system to actually detect changes in temperature. And in many regions of the world, particularly in that kind of mid to higher latitudes, there is significant seasonal variation, and there's kind of temperature inertia, so that when fluid flows across the optical cable, which is based at, say, at the toe of the well, or it can be actually in the core of the not toe of the well, the core of the dam. Okay, we're able to detect temperature, and if we see a significant temperature anomaly, which is related to flow of fluids from the lagoon, which will flow at a different temperature because of this inertia effect, we're able then to detect changes in seepage. And we're able then to measure these points at a very high spatial sampling. Every meter we can measure a flow point. It's got extremely high temperature resolution, 0.01 degrees centigrade resolution, and allows us to have a threshold of measurement as little as 0.01 litre per second. And it tracks the changes in seepage flow. So therefore, we're then able to identify areas where we're seeing significant amounts of flow, which will lead to erosion. And I'll show you a slide at the end of this. This has been quite widely applied now in Sweden. LKAB perhaps are one of the bigger users of this. And then we then go into level 3. This is the strain monitoring using distributed static strain. This is actually a real data set. This is a new tailings storage facility, which we'll see a couple of times in this presentation in Australia. And there are 2 lengths of cable, which are each 20 kilometers length. So we've got the length of cable here, and then also another length of cable here. What this is showing is the baseline strain measurement at the installation of the cable. This is quite a new facility, and we're able to see changes in microstrain that occur along the 20-kilometer length of one of these cables. And this is our baseline information. So then, during the life of the embankment, we'll be able to then see changes that are occurring due to operation of the system, or maybe degradation of the system. And of course, we've got to understand, there's going to be natural compaction and settling of the embankment. So we'll see these effects also in the system. And then we go to levels 4 and 5, where we start to use geophysics. So distributed acoustic sensing acquires seismic signals along many kilometers of fibre. And it's actually equivalent to placing a string of geophones end to end every meter. That's the spatial sampling we can create with optical sensing. And essentially it allows us to provide both passive and active seismic acquisition and imaging capability. So the measurements I've talked about previously are what I call near field measurements, where a change is seen on the optical fibre. But actually when we use geophysics or distributed acoustic sensing, we're actually then able to image. So when we use passive geophysics, we're able to exploit ambient noise interferometry and allow us to look at anomalies that occur over a period of time. And this is published. This comes from a piece of work that's underway in Sweden, where there's actually a test dam. And some of you may be familiar with this. And DAS measurements have been applied on this test dam. And we're able to look at the changes in seismic velocity that occur through the dam over time, and then be able to relate that then to known anomalies, because the dam has been constructed with imperfections in it, as been a reference case, and we've been able to quite effectively identify the known anomalies, weakness points that have been constructed into the dam. And then when we use active geophysics, which does require a source, okay, we're then able to look at the shear waves and the change in stiffness of the shallow subsurface properties, which again are an indication maybe into change of behavior of the materials within the dam. Then that's my wife calling. Not a good time. So then, in terms of the monitoring system architecture, this is somewhat generic. Regardless of the parameter being measured, we're able to bring all the information into an edge computing platform, which is then able to contextualize all the data sets. Each of them, of course, parameters being acquired independently of each other, so it needs to be synchronized in both time and position. And then with the edge platform, then we can provide Internet of Things connectivity, either into a local area network or into the cloud, or also allow remote viewers or operators then to be able to reconfigure the system and of course create alarms. So that's kind of reasonably generic view of able to then gather what are significantly dense data sets, but able then be able to put them into the user environment. And in terms of our track record with this, so over 100 fiber optic systems have been installed in the dams and embankments. Some of these are in hydropower. Many of them are in the mining sector. They've been applied in Sweden, Canada, Australia, and many parts of the world. We have a long-standing relationship with Hydro Research, which are a Swedish company. Some of you may be familiar with them, who developed some of the early algorithms in using temperature to measure changes in seepage flow. And the first installation in a tailings facility was carried out by Boliden in 2000. And then since then, over 200,000 meters of cable has been supplied into the dam sector. And one of our activities during COVID, and I think that's been a great achievement for us, is able to remotely supervise the commissioning and installation of our dam pulse system in a new tailing storage facility in Australia, where over 20 kilometers of fiber was deployed during the pandemic. And cables have been placed, or will be placed as the dam develops into the drain, into the crest of each of the areas as they build out the dam, as shown here. And then moving to closure of the presentation, this is just an example, gives a kind of an understanding of the kind of extent of this work. This is Kiruna in Sweden. Many of us are familiar with Kiruna, and we see how the system has evolved over this period of time, and significant numbers. I would say that the Swedish sector have been probably more aggressive early adopters of this technology than some other parts of the world. And then two of our current projects, I have spoken about this one previously. This is the storage facility in Australia. Many of these areas are somewhat sensitive, so I'm not allowed to disclose the name and location of the operator, but there are two lengths of 20-kilometer fiber placed into this. We've collected the baseline data. And then this is in a slightly different sector. This is a well-known piece of work that's underway now in British Columbia for BC Hydro. This is a new hydro barrage being built on Peace River, which is in northeast British Columbia. If you go onto Google Earth, you can see this thing. It's huge. And we are now midway through the process of laying sensing cables in the core of the structure. And when it's completed, it will look very much like this, with an earth-filled dam. And this will, both these systems have the complete array of measurements, which takes us really from the dam breach right through to the geophysics. And then my last slide really is to say, well, how does this fit with existing conventional technology? Clearly, I think we complement all known systems, because essentially we're able to fill in the gaps, because we are a high spatial density system. We're able then to measure with perhaps greater resolution, particularly in terms of microstrain rather than millimeters or centimeters. And I think also there is significant potential to perhaps substitute for many of these conventional systems too. But obviously at the present time, our focus is very much on proving the technology and getting acceptance on the reliability, because these are obviously very mission critical installations. But I do feel in the longer future, there is an opportunity to substitute. I think, Mike, that takes me to the last slide. Yes.